Good morning, everyone, and welcome to the Illinois Sustainable Ag Partnerships virtual series on the leading edge conservation drainage practices for nutrient loss reduction. My name is Adrienne Marino. On behalf of ISAP, and especially on behalf of the Conservation, Drainage Industry Agency, and research partners engaged in developing this meeting series, thank you for taking the time to join us today. As we're getting started, we invite you to fill out our intro poll by going to menti.com on your smartphone or in a different browser window. We're going to come back to that poll in just a couple minutes, but the code here is in the chat and also on the screen. The Illinois Sustainable Ag Partnership works to promote a whole systems approach to agricultural conservation. The 12 members work collaboratively to provide consistent technical assistance to Illinois farmers and advisors on soil health and conservation drainage practices. You can visit our website at ilsustainableag.org to learn more about our partner organizations, our programs, and other opportunities to engage with us. A quick moment for housekeeping in advance of today's meeting. First of all, today's meeting is being recorded. We'll post the recording to ISAP's website as well as provide a link in a post-meeting email. Second, we'll be using the chat function in a number of different ways during today's meeting. As we're getting started, please feel free to type in your name and organization to help us and others participating know who's joining today. Please also use the chat function to report any technical or audio issues, as well as to ask the speakers questions. We'll be monitoring the chat for these items, and our speakers will address as many questions as possible during the allotted times. All participants have been muted upon arrival, so please remain muted to minimize any background noise. However, since we had envisioned holding these meetings in person to enhance the shared learning experience for everyone, we do invite you to keep your cameras on if you're willing and able to do that. And finally, we're going to be incorporating some interactive elements into the meeting today, and one of these is Annotate. I'm just going to give a really quick overview of how to use Annotate, and please only use that when you've been asked to do that. But if you go up to the top of your screen where it says you're viewing my screen, there's going to be an option to view more options. If you click that, you'll see Annotate, and it will show up with a larger toolbar here. We're going to be primarily using the stamp feature of Annotate. All right, I'm going to quickly go back and see the results of our poll. And it looks like there is high interest or moderate interest in a lot of the topics that we've laid out here. So that's great. We're going to work to incorporate this feedback into our next 2 sessions and also into any follow-up that we can provide to you. So thank you for that feedback and for offering that today. Let's get to our agenda for today. Our first speaker is Dr. Jane Frankenberger, who is an Associate Professor of Agricultural and Biological Engineering at Purdue University. Dr. Frankenberger also leads the multi-state, highly collaborative Transforming Drainage Project. Jane, thank you so much for sharing your time with us today, and I'm going to turn it over to you to share your screen and begin your remarks. You are muted. There you go. Perfect.
That's right. Thank you. I'm so pleased to join everyone at this first session of the series that's called On the Leading Edge, which I think is a great name to describe what we're trying to do. Because moving towards conservation drainage is not really getting people on board with what's in the mainstream already of conservation practices, but to be leaders in thinking about what people can do and what's needed if we're going to solve our nutrient issues. So I'm happy to share my thoughts with you today as one who's been working in this area for many years. I'm based in Indiana at Purdue University, but I've been working with Adrienne Marino and other leaders of this effort through the Transforming Drainage Project and others. So with that, I will share my screen. And okay, so this is the title I gave, so you can see the start to my title, Managing Water for Tomorrow's Agriculture, and hopefully it will give an overview to the opportunities and challenges that we have, and then the other speakers will talk more in depth about some of the practices. So as you all know, managing water is key for agriculture in our flat, rich soils, and excess water is the most common issue that we deal with. So we've installed subsurface drainage for many years, back from the time when the term tile drainage actually made sense. So I'm happy to show some of the photos that I recently found in the attic of our agricultural engineering building that show where we got to this point. And I'm sure you also know, but just as a review, what drainage is doing is, oops, well, okay, I don't know why it didn't go there, but it's lowering the water table so that our crops have enough aeration below the root zone. Oh, now it's good. Okay. And it's very common across the whole Midwest. I wasn't sure if there were people here from beyond Illinois, so I'm showing the whole Midwestern image of where we think that drainage is likely based on a number of landscape features. And so we've made a drainage infrastructure that's designed to get rid of water as quickly as possible. Sorry, this still says Indiana. It's certainly common across the entire West, but I think you'll agree this is what most of our farmers are thinking, that we want to get water into the tile drains, into the ditch, and then it's going to flow away. So from the point of view of the local farmer, it's that the water goes away, but we know it doesn't go away. It goes into streams and rivers and the Gulf of Mexico. And there's several issues with a single-minded focus on getting rid of water as quickly as possible. And the first one is flooding. Now, it's certainly not drainage that leads to flooding, but it's that if we don't make any effort to store some of the water, as we'll talk about in a minute, if we're just getting rid of it, people downstream are receiving it. The second one, and I think it drives a lot of what we do, especially in the conservation community, is that we know that our nitrogen, that drainage water, when we see it, doesn't just have water, even if it looks fairly clear, it's actually got nitrogen in it always, always, always. And what we've realized more often is that it also has phosphorus in it. So the water that looks clean is still leading to substantial water quality issues downstream. And the third issue that's not always so obvious because the excess water problem is such an issue is that that later in the summer, when we sometimes have dry periods, we can reduce crop yields and stream flow. So before we talk about how we're going to deal with that, I just want to step back and in one question say, as we're looking to the future, how do we expect this to change in the future? And as we think to tomorrow's management challenges, the bad news is that all three of those are going to get worse. They're not going to stay the same and they're not going to get better because of the increases in extreme weather that happens during the winter and spring. So our winters and springs are becoming wetter, and so that increased flooding will continue to increase and nutrient loss will continue to increase, while our summers are unfortunately getting drier since the rainfall will be more intense, and also because of the warmer temperatures, the crops need more. So it's bad news looking ahead, which is just more of an impetus to do something different than the way that we always do it. So when we think of too much and too little, hopefully the concept that comes to everyone is the idea that we need to think about how we can store drained water in the landscape. So it's sort of an obvious thought. That's the focus of the project that I lead called Transforming Drainage. But we'll talk about, more importantly, is how we can get some of that drainage to happen. So this project with people across the Midwest have a vision of changing the way that we design and install drainage so that we can include more water storage and even water recycling. But what I want to do here, which I haven't done before, so hopefully it'll work out, is show a little video that we made. It's a 2.5-minute video that explains this concept, I think, better than I can in 2.5 minutes.
Like all farmers, Joe knows the value of having a steady supply of water throughout the growing season. Not too much, not too little. But in recent years, he's noticed a change. Again, this past season, a particularly wet spring was followed by an especially dry summer. And this pattern appears to be happening more often. To deal with too much water, Joe has invested in drainage systems that have helped ensure he can get the crop planted and fertilized. But when that thermometer starts to rise and the plants start to curl, Joe's beginning to wish he'd kept some of that water he drained away. But how would he store water? Meanwhile, downstream in the town of Riverdale, Joe's cousin Ed, who serves on the town board responsible for drinking water, is concerned about the high levels of nitrogen and phosphorus. Because he is also a farmer, he understands the necessity of drainage, but he also wants his grandkids and neighbors to have clean water. Joe understands Ed's concerns, and the idea of storing or retaining water really has him interested. It could help the town of Riverdale solve their water quality issues and increase crop yield for him during hot, dry summers. But how could he store the water? He knows that
Oops, sorry, I thought it was great.
the soil already stores a lot of water. But what if it stored more? Instead of draining it all, he could stop drainage after his fields had been planted and spring work completed, leaving more water for his crops in the soil during summer months. But what if storing water in the soil wasn't enough? What if some fields could benefit from more water? Maybe he could build a pond in his field down the road, where he could store water in the spring when the tiles are running. Then he could irrigate it back onto the field in summer when the water is needed. Although this would be a big investment, Joe is not one to shy away from a challenge. He knows he will get higher crop yields. And because he's reducing nutrient loss, the cost would be shared by taxpayers. And by working with the local university, which is studying more efficient storage methods, he could possibly reduce his costs even more. His neighbors see what he has done and realize that they could store more water on their farms as well. As a result of all the water storage upstream, Riverdale's water system has higher quality water, which makes Ed and the people of Riverdale happy. And Joe's happy because he now has water available throughout the growing season. To learn more, go to transformingdrainage.org.
Oh, okay, hopefully that worked okay. It's my first time to share a video of the screen, and I suddenly thought, oh, maybe I should be muted, but clearly that wasn't the way to do it. But that's, I think, a fun video, explains the concept that we're getting at, and any of you saw that it was on YouTube, and so anyone can use it in your work with whoever. So it's up on YouTube and accessible from our Transforming Drainage site. So now we're going to turn to not the concept, but what can we start to do? And again, I'm just giving a broad overview here and thinking about the big picture. I think you'll agree this is a typical drained landscape. It's not obvious where we can store water, but some of the places that appear are in the field itself, in the buffer, and in the ditch. That's some of them. So I think we'll just start out sort of walking through the different places that you can think of that would store a field and get at those three benefits that we're looking for: the decrease in peak flows, the nutrient retention, and saving water for the summer. So soil health is very big right now. Anybody who's working in conservation certainly knows that soil health is the push through NRCS and so many other organizations. And soil health can increase the water storage capacity of the soil. The bad news is it doesn't do as much in our rich soils of the Midwest, which are already so good at holding water. It particularly works with lower quality soils, but there's a little bit of benefit that can come that way. So it's certainly something that we encourage, and cover crops and similar practices are just important for water quality in general. We can also store more water in the ditches. There's a concept called two-stage ditches, which you widen the ditch to form these benches, as is shown here, and there's good nutrient recycling in that. They kind of become little wetlands and also have the potential for more storage. Not a lot, but some. So just listing all of them here. Another way to store water in the field is through actually holding the water in the drainage system. So that's called drainage water management, or also controlled drainage. You will hear both, more controlled drainage with the research community. Drainage water management is the official name through NRCS. So the idea is that we raise the boards, the outlet, through using a water control structure after harvest, let it down before planting or harvest so that there's no impact then, and then after planting we can raise it probably to a lower level, but that way we can store some water for the crops. And we've been doing a lot of research on it, but I think you're going to have a presentation on that soon. There's another practice where we could potentially store it in the buffers. So here's the idea that in a conventional tile system, it goes right under the buffer, and the nitrate is lost that way. But if we instead put a control structure in and distribute it to the saturated buffer, denitrification can take place and treat much of the nitrogen. So that's another possibility. And then sort of the biggest possibility, but the most difficult to do, so the least actually done so far, is can we store the water in a pond or a reservoir and then recycle it back onto fields? So this is the idea is that drainage now, instead of just going downstream like that image that I showed earlier, we're actually going to capture it in some kind of a pond or reservoir and then irrigate it back onto the crops at the time that they need it. So this has the great advantage that it's not only the water that goes back onto the crops, but it's also the nutrients. And that's a practice that we're calling drainage water recycling. So this is not very common. This is definitely the leading edge. We're looking for places to implement it more, but there are a few examples. This is a place in Michigan where a farmer started out with one drainage water recycling pond after it was a borrow pit for a highway that went through his field, and then he liked it so much he built several more, as this one. Here's an article about a farmer in Iowa who has done it. These are not small ponds, so don't mistake that a little farm pond out in back is going to do it. This is a very large example from Manitoba, but to really make an impact on flooding and on nutrients across the Midwest, we either have to have really a lot of ponds or they have to be quite large. But farm policies, our agricultural policies, could be changed so that that becomes more beneficial for people. Also, just to look at crop insurance, if you haven't seen this before, I'm sure it's the same in Illinois. There's a lot of payout for flooding and excess moisture, $930 million in 25 years, but there's even more for drought. So if there's a practice that could help both of those, that can certainly be beneficial. So storing drained water in the landscape is key. But as I said before, we've got these very flat lands, and so it's not always obvious where we are. And one practice won't work everywhere, and so we need to think of all the multiple benefits, and then we need to identify opportunities where we can store drained water in our landscape. So if I look at a landscape like this, where can we implement practices? Well, in almost every field, there's an opportunity for soil health, right? To do practices for soil health. That's the universal one. Where we have drainage, which is probably everywhere in our really flat landscapes, we can put controlled drainage or drainage water management. Where there's a buffer, we can make it a saturated buffer. And where there's some kind of opportunity to hold water, we can do drainage water recycling. Now, there's one practice that you're talking about today that's just not part of our practice, and that's constructed wetlands. So I certainly want to include that as well. It just doesn't happen to be in my slide here, but constructed wetlands is another way of retaining more water in the landscape, which is so important. Okay, so you saw that. Now, as Adrian brought up at the beginning, we're going to try using annotate. We'll see how this works. But once again, you click at the top on view options and then annotate, and then you'll come up with this toolbar. And then here is a question. So everybody's going to do this now. So get out your annotate. This is the time. And go to the stamps area. You can go to arrow if you want, but if you want to do stamps, put your stamp on the correct answer on this slide, and we'll see how that works. Okay, I put it in the middle so you got plenty of room to the left, but it looks like everybody's got the concept. That is right. So no-till is not going to help us store drainage water in the landscape. Okay, so that easy, but anyway, you got used to doing the annotate. So now we're going to do something a little harder. Oh, we're going to have to clear all those. How do I do that? Oh, Adrian is going to have to clear them. So, okay, so clear those, and then we're going to do our next exercise, which is to look at a landscape that I have picked at random, almost at random, from Indiana in Google Earth. And we're going to try the same exercise now as what we showed you, of your turn to think about where we might put in one of those storage measures that you just saw again, right? So there's controlled drainage, saturated buffers, drainage water recycling. I think I'll zoom in a little bit further. So it's a pretty typical landscape, I think, for Illinois and for Indiana. Look around and put any kind of a mark, your X, your heart, whatever you want, on any place that you see as a potential conservation drainage or drainage water storage location. Okay. We have a number that saw the little buffer there along the ditch. Okay, that's great. Okay, I like the people who have used a heart here up at the pond. If you didn't see that one, well, I shouldn't probably go back in. But there is a pond that already exists here. Now, I don't know why that pond exists, but I think it's because of the interstate that goes here. So probably was part of the construction. But it's just sitting there. That provides maybe a low-cost opportunity to do some kind of drainage water recycling. I'm going to speak for you. I don't know if there's anyone who wants to type. I'm actually going to open the chat here now and see if there's anybody who wants to type any explanation of what they put on in our little landscape here, in our sample landscape. And with that, okay, I don't see any. So some people have put here, I'm going to have to assume that this is either soil health or some kind of a controlled drainage kind of practice. Some of you may have noticed that this is in an area that has a wind farm. So just in case, it's kind of unique that way, and the aerial photo does show the wind farms. Otherwise, it's just a very typical landscape. All right, so now, Adrian, I guess we need you to clear the annotation again. All right, so hopefully that got you thinking about the opportunities. Now I'm just going to switch to thinking about how we're going to scale these up. Our project, Transforming Drainage, is a large-scale project just ending, but what it's been focusing on from all these universities and others, a lot of collaborators that are not listed here, is a number of field sites and then putting some tools together. So I'm going to, I guess I'm going to go, well, I'll at least show you the sorry, okay, the website. I think I've got time to at least show it to you. So there's the home page, and then we have these tools here. And one of the tools that I thought might be useful is one that we've just put up that gives where we think drainage is the most likely. And you can zoom in. It's a very fast website, and you can look and see where drainage is already likely to occur. So that's not really a transforming drainage tool. That's just drainage. Then we have one that's about where controlled drainage is most likely to be effective based on a number of properties that you can go there. And then we have a new one that's looking at sub-irrigation, if anybody is interested in that, looking at where sub-irrigation might be a possibility. The green areas are where it's most suitable, so you can sort of get an idea of that. So I'd be happy to spend more time on that, but I think I'm gonna make sure that there's a little bit of time for questions. I hope there will be some questions. So we have the tools. So let me just close again. I'm happy to show more of that. But the benefits, again, of storing water in the landscape are both on the side of reducing the water-related risk, the water availability, the water quantity, and reducing the nutrient losses from agricultural fields. So that concept is what we need to work towards as we think about not just today's agriculture, but working towards tomorrow's agriculture. Again, when we see the drainage, we've got nitrate and phosphorus coming out. Ideally, what we want is them to not go downstream, but go back to where they're not only not harmful, but they're actually beneficial. We need those nutrients. They're important. They're critical for crop growth, and we want them to be taken up by the crops. So I think I'll end here and see if there are questions. And I'm putting up the URL for a new drainage site that even more than transformingdrainage.org, which is a project that's ending, we have a region-wide group called the Conservation Drainage Network, and its URL conservationdrainage.net is what we're trying to make. It's still in its early stages, but we're trying to make it into the go-to spot for all kinds of information on conservation drainage. So you can interact with it. There's an email there to send to the whole organizing committee. There's 9 of us that are on a committee from a variety of agencies. The Ag Drainage Management Coalition, the industry group, and universities. So with that, I will thank you, and looks like I've got about 4 minutes for questions, right?
Yeah, thanks, Jane. We did have Sarah put a comment into the chat that I thought was really pertinent on your level example there, but she said it's also really great to think about converting some of those smaller fields that might be hard to farm, as those might be opportunities for where to put some of that water storage.
Yes, you're so right, Sarah. And I started looking around Google Earth. We haven't done a lot of this to look for opportunities where there is an oddly shaped field. There was one where, in fact, the Nature Conservancy was going to work with people in Ohio, and there was a field that had a road on 2 sides and then a ditch. So it was actually difficult for the farmer to get into. And that's the kind of thing that would be perfect. I think that there's lots of opportunities as you folks talk with your audiences, whoever they are, to think about opportunities that would be the most beneficial, that really have an opportunity to work with that. So thank you for pointing that out, Sarah.
And then Keegan has a question from Iowa. What funding sources are available for a farmer looking to implement DWR?
Okay, so that's
water recycling.
Yes, exactly. It's good. So hopefully everyone knew that already after this presentation. That one is the newest, and so it doesn't have a NRCS standard that's been in place, and consequently it doesn't have cost share funding so easily available for many of the states, but they have made it available. There has been a 319 project in Ohio, again, that funded it. It hasn't actually gotten implemented yet, but they were able to do that. But the good news is that we've been working with NRCS to get a new, well, it's actually a revised standard, and it's called, so yet a different name, it'll be called irrigation and drainage tailwater recovery. In that will be drainage water recycling. But I think it's close enough that I should start putting that in my talk. So that's a good reminder. These new NRCS standards, they've been in the Federal Register since last fall. They're all approved. They tell me that they're going to go up, be official any day. And this is July, so I think it should. And then each of our state NRCSs through the State Technical Committee will decide whether that becomes available in your state. So probably over the course of the next year, there will be a lot of movement there, and that one will become available. Then I don't know about your state, but in our state, the 319 program bases the standards that they can pay for on what's available there. Note to myself. So great question, Keegan.
And we have Ruth, our local NRCS expert here in the chat, mentioning that she's calling it the irrigation and drainage tailwater recovery.
And if you have any questions, definitely ask Ruth Book. She is the authority, and she's the one we worked with. So thank you again, Ruth, for all your work on that.
And Adrian, I don't know if we'll have time for this one more, but we have one more question from Katie Walsh coming through.
Why don't we flag that, and we can ask that at the end if we have additional time for questions, just so we can keep to our schedule. But thank you, Jane, very much for those remarks. And next, we're going to move on to our next 2 speakers who are going to cover the science behind a suite of conservation drainage practices. Nathan Utt is a doctoral student with the University of Minnesota. He is based in Eastern Iowa And he's going to be sharing from his more than 10 years of experience in the drainage industry. And following Nathan's presentation, Dr. Jill Costell from the Wetlands Initiative, she's their senior environmental engineer. She's going to present on the constructed wetland practice. So Nathan, why don't you take it away? And then as soon as you're finished, we'll go to Jill, and then we'll do questions for both of them together. And Nathan, you are still on mute.
That was a rookie mistake. Oh man, I can't believe. Thank you. Thank you, Jane, for your presentation. Once again, my name is Nathan Nutt. I'm with the University of Minnesota, but actually based in Iowa. So actually just across the river from Illinois, on the other side of the Mississippi. And kind of the goal for my presentation today is not so much to talk about the details of how to implement these different practices. that will be covered in a later seminar in the series, but to get more at kind of what's working behind the scenes to actually make these practices work. And as Jane mentioned in her presentation, there are there we go. Drainage is a really important part of our cropping systems in the Midwest. Well, it's an important part of all plant growth for the most part. And while there's lots of water quality benefits from drainage systems, there's also some of the downstream impacts that we want to avoid. And there have been a lot of different practices that have been developed, both in field, with how we farm, with how we drain, as well as edge of field practices to really address these concerns. And Jane mentioned a few of them in her presentation. And the ones we're going to focus on, Jill and I, are honestly just 4 out of the many to choose from. We're going to talk briefly about controlled drainage, which Jane covered a little bit. We'll talk about bioreactors, constructed wetlands, and saturated buffers. And Jill is the expert on constructed wetlands. I'll leave that to her. And I'll talk a little bit about the other 3 where I have a little bit more expertise. So how do these different methods actually help us reduce the transport of nutrients downstream? And there's really, it seems obvious, there's 2 main ways. You either reduce the total volume of water with the dissolved nutrients in it that's leaving the field, or you reduce the concentration of those nutrients within the water. And now these practices all kind of can do a little bit of all of these, but controlled drainage, as Jane mentioned, really has the water quality impact as far as nutrient transport by reducing the drain volume. And then the other 3 practices that we'll be talking about don't really reduce the volume, but they have a big impact on the concentration of nutrients within those drainage waters. So we talk a lot about nitrogen and phosphorus both being nutrients of concern, but a lot of these practices are really targeted at dealing with the nitrogen issue. And the reason for that is not that we don't care about phosphorus, we do. It's just that they behave very differently as they cycle through the environment. Phosphorus, if you want to remove it from water, requires chemically binding to something, to some sort of a substrate. Like it can bind to the soil, which is what we like it, because then the plants can use it, or it could bind to other materials that we sometimes use for filtering, such as iron ore slag. One of the difficulties is those materials only have so many spots where the phosphorus can bind, where it can stick. Once all those locations are full, we've now reached the maximum capacity of that media, and it either has to be refreshed or we're just done, and then we can't go any further. And we also run the risk of, if there's a change in pH or other things, you can now release some of that phosphorus again, so it's a little more complex. But nitrogen, on the other hand, isn't removed based just on chemical binding, but it's actually biologically degraded and removed from the system, which is fantastic. Which means that when we're looking at trying to remove nitrate, if we have a system that can do it, it can basically continue indefinitely as long as those conditions are continuing to be met. Now, I will add that nitrogen and phosphorus can both be removed by plants through plant uptake, but that's not really seen as a long-term loss for the removal from the nutrients, because once those plants die, they'll decompose and those same nutrients will be released again into the same system. And so unless the plants are harvested and removed, there's really not a long-term gain just from plant uptake. So that's why that one doesn't weigh too heavy into the long-term use of these practices, once again, unless there's a harvest component. So I've been talking about this magic of removing nitrogen from the water, and it's basically just due to a lot of bacteria that live in the soil. And under anoxic conditions, when there's no water, when there's no oxygen within soil water, they respire or they rebreathe the nitrate, converting it to nitrogen gas, which just goes up in the atmosphere, which is most of our atmosphere anyway. So literally all our problems disappear into the wind, and it's fantastic and it's beautiful. And I love little microbes, even though I never get to see them. Well, most of them are pretty good. Some we don't like, but anyway. So what do we need to do to make those little microbes happy so they will take care of all of our problems for us? That's what we want to know, right? So what they need to be happy and to do what we want them to is to, first you have to have a saturated soil, because that helps reduce the available oxygen. We need a carbon source, basically need food for them to munch on. We need some nitrate for them to respire. We need a little bit of warmth to keep them active, and we just need a little bit of time. We just need to give them time to do their job. So that's how we get rid of the nitrate to the denitrification process. Now I want to switch forward and look a little bit at controlled drainage. And Jane talked about this with her presentation, but the basic premise is if we don't need to drain, we don't drain. And we store that water within the soil profile. So if we don't need the water table down low, we can keep it up high. And then that enables us to store the water. And by storing the water, we store the nutrients that are dissolved in that water in the soil profile as well. And she talked about how we kind of manage things differently throughout different needs during the growing season, kind of the need of the plant and the environmental need. And this practice is really proven to be very effective when it's implemented properly. And like Jane talked about, it's really reducing the volume of water leaving the field is what's causing the downstream benefit. And this practice has been studied for quite a while, and the annual reduction and nitrogen leaving the fields can reduce from 15 to 75%, depending on the system and the weather that year. But a 30% reduction in nitrogen loading is very typical for these systems. And they do have the potential for on-farm benefit, which is, we can't say that for all conservation practices. So I want to point that out when I can. So there's potential for a little bit of a yield increase depending on how the system is managed and what the weather patterns are like for that given year. Some of the limitations to adopting this is that you have to have a really flat topography in order to make it work effectively. After a couple feet of elevation change from the control structure, you're really not getting the management to the raised water table that you're going for, and so you've lost the ability to really do anything. So that's why flatter topography is really critical to helping it work effectively and cost effectively. Another limitation is it does require management by the farm operator throughout the year. And while it's not a lot of time, that is a concern that some producers have, is they just don't want to take the time, or they're going to forget perhaps to pull things out or to reset the stop logs after they're done planting or after harvest. And so there's a lot more room for things not to operate as well as they potentially could, as compared to other practices where you can more set it and forget it. And another limitation is that they have to be in free flow period during the spring to prepare for planting, which also coincides with when we have a lot of heavy spring runoff, where we want to have more treatment and storage if possible. And so a drainage system, controlled drainage system by itself kind of has that as a downside, but over the course of the year, they're still really effective, as I mentioned, reducing the overall nitrogen load. All right, so keep moving forward. We'll talk about bioreactors. And to me, these are the fully engineered. We can design it to do what we want. You know, we can really control a lot of the design parameters with this compared to the other practices. And these are the way these systems are generally plumbed is you'll have a control structure shown on the left on your screen, similar to that used in drainage water management or saturated buffers. And that structure is used to divert water into a separate chamber filled with wood chips. Now these trenches could be anywhere from 10 to 40 feet wide, or maybe 40 to over 100 feet long. So they can get rather large depending on the design needs for that site. And then, so the water is diverted into the wood chip trench, and then it exits through an exit control structure that sets another elevation for the water levels. And then the water either discharges directly into the ditch, or it could be tied back into the main that it was pulled from, whatever is needed for the design to work out in that specific site. And the way the bioreactors create the denitrification environment that we love. Now remember, what's denitrification need? Carbon source, saturated soil, or wood chips in our case, needs the nitrates, some warmth, and some time. So we're giving them the carbon source via the wood chips. We're saturating the wood chips using the stop logs in the control structure. So we're able to set a high water table at the inlet and then have it lower at the end for the water to drain out. And the next part is, well, I'll get to the warmth in a bit. The next part is the time. And so the way we set the time is based on the hydraulic gradient of that particular buffer, which we can design because we know how fast the water moves through the wood chips. And so then we can, by adjusting the elevation difference between the inlet stop logs and the outlet stop logs, we can set how steep the water level difference is. The steeper water level would be a steeper gradient and it moves faster. And then it's also impacted by the length of the chamber. And so a longer chamber takes the water more time to move through it. And when we're designing these, we want to, it's a balance. You want it to move through as quickly as possible so that we can get as much water treated as you can in that space. We also want it to go slow enough that the bacteria have time to actually fully complete that denitrification process. So that's it's one of the design balances with these systems. And so how do these actually help with the nitrate load reductions? Well, they don't change the volume that's leaving your field. So your field's going to drain as much as it did with or without the bioreactor, but the concentration of nitrate will be reduced that's in your drainage water. Now, these things can also be really effective. They've been anywhere from 12 to 90% annual load reductions from the drainage systems, but the 30 to 40% load reduction is more typical. Once again, but that also depends a lot on how the system is designed. And you'll see a lower reduction if it's a very large drainage system, but you only have space for a small bioreactor, right? You get a low percentage of load reduced, but you might still have a high, say, final pounds of nitrogen removed because you've got such a large treatment area you're covering. There aren't really any on-farm benefits from a wood chip bioreactor. One of the limitations is that you can really only treat base flow conditions. Just from a practical perspective, you can't make these things big enough to handle the peak flows from a big storm and a tile drain system. But so when there's one of those high flow events, most of the flow is going to bypass the bioreactor and not be treated. However, tile drain systems tend to have a lot of base flow, and so there's still a lot of treatment that occurs throughout the year, which is why they're effective. As I mentioned, those little soil microbes love to stay warm and cozy, so they keep working efficiently and happy. And so when it gets cold, especially below 40 degrees Fahrenheit, they really slow down and are no longer doing much. So they don't work as well in cold weather, which is one of the limitations of these. But I'm going to include in my limitations a major selling point that the other ones don't have is within some practical limitations, these can be engineered to fit into most landscapes. So a lot of the topographic constraints we have with the other practices can really be designed around to some extent with the bioreactor. So that is one of the really big strong points of this particular practice. Awesome. Now we'll move on to saturated buffers. I don't know if I can have a favorite or not, but this is one of my current favorites. Hopefully you guys, no offense to the other ones. I might get in trouble later for saying this is my favorite, not the other ones, but this is my, all right, I'll move on. So in a regular drain system, right, you have the laterals that tie into the main drain, which goes, you know, through the field, right underneath that beautiful buffer and into the stream. And the whole goal of the saturated buffer is to reconnect the tile water, subsurface tile water with the subsoil in the buffer. So put a control structure similar to the other practices on the main. We run a distribution line, which is just perforated tile underneath the buffer. And now instead of the water flowing directly to the stream, it's diverted through the distribution line. And the control structure helps raise the water table and push the water laterally through the subsoil. It's not flowing over the top, but it's flowing through the subsoil and towards the stream. And when it does this, it behaves just like a bioreactor, basically. So a bioreactor, we've got, right, so we've got a hydraulic gradient. So on your left, it represents the field side. We set a high water table based on the control structure. The ditch would be on the right, so that's for our outlet. And in a bioreactor, we're using usually wood chips as our carbon source. In the saturated buffer, we're actually using the organic matter in the soil as our carbon source. And so what we do is we, right, similar to the other practice, we're trying to create denitrification conditions. So we use that distribution line and control structure to raise the water table within the buffer, and that brings the water up into that layer where there's the soil layer where we have the organic matter where the microbes can feed. With the raised water table, we reduce the oxygen, so we're going to start denitrifying, and they've also created a good hydraulic gradient to help push the water through the system to try and maximize the treatment that we can with that buffer. So they behave similar to the bioreactor as far as the theory behind how they operate. It's just that we rely more on the natural environment to do the work for us rather than a fully engineered system. So similar to bioreactor, we don't really see any reduction in the flow volume that's leaving the field, but we see a major reduction in the nitrate concentration of that drainage water, and that's where our load reductions come. So these are honestly in a very similar range to the bioreactor, 70, 90%, over 90% annual load reduction. More of a 40% annual nitrogen load reduction is fairly typical. No major on-farm benefits. If you're doing hay production or something in the buffer, there might be some benefit from increased available water, but that might be fairly minimal as far as an economic benefit. Limitations similar to the bioreactors, you can't treat high flow. It just isn't the capacity of those systems, so they'll bypass. Inefficiency decreases with cold weather, once again. And the other site-specific restraint is they have to have a flat topography along the stream itself. The field can be sloped, it can be undulating, that doesn't matter so much. It's mostly that the buffer itself needs to be flat, and that's the main limitation for implementation, as well as some soil things and so forth, which we talk more about in the future workshop. So I think I've used up all my time, so I'm going to just conclude my portion of this segment. So the nitrogen load into our streams through these conservation drainage practices are really done through two pathways. We're either reducing the drain flow through controlled drainage, or we're reducing the nitrogen concentration in the drainage water without really changing the drain volume. And that's where the bioreactors and the saturated buffers come in. And the reason we're doing a lot with nitrogen instead of the phosphorus is just because there's a biological mechanism that works really well for moving the nitrogen. And the phosphorus is just a little bit more tricky to work with. There's still ways to do it, and we're working on it, the nitrogen is much more, it just works a lot simpler, more straightforward. And all of these practices, really fall in that 30 to 40% annual load reductions for a well-designed, well-functioning site. So that's all for my part of the presentation. I'll turn the time over to Jill to talk about wetlands.
All right, just get my screen share going here. All right, so guess what my favorite practice is? I only have one, and that's a constructed wetland. So it was really nice that Nathan set up a lot of this, the information, so I don't have to necessarily repeat it, but I'll just put it in the context of a constructed wetland. So we'll start off first is what is a constructed wetland? Well, it is not a restored wetland. Constructed wetlands are artificial ecosystems designed and built specifically to treat water. It could be wastewater, stormwater runoff, in our case, tile drainage. They are engineered systems. As you can see here, we are essentially diverting a tile flow into a very shallow basin to allow the processing to occur. How does a constructed wetland work? Well, Nathan covered a lot of the things, what the things we need in there. So essentially the tile water is providing that nitrate load. The microbial community in this case is attached to the sediments and the plants at those surfaces, and there are oxygen gradients on those surfaces, just enough to form that anaerobic condition that we need for the bacteria to use nitrate as they're kind of breathing in the absence of oxygen. The carbon source in this case is coming from the plants, the plant roots, the accumulated decomposing plants, algae, fungus, other organisms within a wetland system. And often in these systems, you can have carbon as the limiting factor. And as Nathan mentioned, plants are just temporary storage. They're nice, they grow. Unfortunately, when they die off, they release most of the nutrients that they have absorbed. So what are the conditions for denitrification? And I didn't even know Nathan's presentation ahead of time, but I think we covered some of the same things here, not in the same order. So we need nitrogen. We need the bacteria community, and it's there. It's available in all soils. But we need to give it such that it has a substrate, something to hang on to, and provide that anaerobic condition. We need some carbon that is biologically available, so it's available for the bacteria to use. And initially in a wetland, that's often the soils. Because you were using essentially what was the topsoil on your farm field as the growth media within the wetland. Unfortunately, this gets utilized pretty quick, and it's pretty low generally in terms of what's bioavailable. So over time, the plant community, as it's dying off, the algae, other things are adding to that carbon source and making it bioavailable. So over time, you'll see wetland sediments kind of grow in the organic matter and what we call the labile fraction, the bioavailable fraction. And of course, we need time. We need contact time for the community to process the carbon and nitrate. How do we achieve it? Well, we build a shallow water holding basin and we add tile water to it. And adding that water forms that anaerobic condition. And we need to hold that water for a while. So how do we, decide and how long do we hold it? Well, you want to hold it maybe 3 hours to 7 days. It's really variable based on tile flow and your nitrogen concentrations coming into that wetland. So we use kind of a shorthand technique to kind of figure out how much residence time. And what we use is the wetland to watershed ratio. So you want the wetland size to be at least 1 to 5% of the area that you're capturing. So if you have 100 acres that are pattern tiled, you need at least 1 acre of a treatment wetland in terms of the treatment area. So there is, it's going to take land out of production here. I would recommend around 3%. I think we're finding really good results around 3% in terms of efficiency. The shape does kind of play a role in everything because we want a really long flow path as that leads to that contact and opportunity for the microbial community to do its job. And water depth is key here for a couple of reasons. One, it promotes the emergent marsh vegetation that we want. We want a nice, fairly dense community there since it's our carbon source. And it also allows provide a warm environment. So in our case, our heat is really coming from solar energy. So if we have a shallow system, the water will warm up fairly quickly. The bacteria are happy, they're removing even more nitrogen. So usually in the late summer, we see our most production in terms of reduction. And wetlands kind of reduce a little bit of that volume flow because we can store some water, and during the summer, we have some evaporation and transpiration. So, you know, we do reduce the volume a little bit, but it's not necessarily being designed to hold large stormwater events because we want to get back down to our operating level. So the NRCS practice is 656, and because this practice is using the best available sciences, it's using a lot of those design factors that we talked about. Some of the highlights are you're just essentially building a shallow pond, or you're building a pond and just not filling it up. And you use a water control structure like in the other practices to maintain your operating water level, your pool, and also allows you to change the water levels in the very beginning to get your plant community established. And you really want to kind of maximize a hydraulic retention time and flow path within reason. You don't want to make the wetland too big because you're not going to get additional removal, but you don't want to be so small that the water's just flowing through too quickly. So it's kind of a little bit of the Goldilocks. You want the thing that's just right for your situation. And then under 656, there's a specific guidance for tile drainage, water treatment. The main thing here is we want to daylight the tile, and we want the normal operating pool just below the tile invert for not impacting drainage upstream. You want the 50% of the area should be 12 inches or less. This is what's making that really shallow system that we want. And the treatment area needs to be at least 1% of the contributed drainage area. If you have surface water going into your wetland, you need to account for that as well. Usually I just focus on the tile drainage, put a little berm around your wetland, a little embankment, because that's what you really want to treat. We don't have a lot of nitrate coming off the fields. So conditions for implementation, where can you put these? Somewhere we have sufficient tile drainage and you have a tile that you can divert into a wetland, and an area for it. You know, maybe that weird corner or that spot that's a little hard to farm. We preferably have it on your low non-profitable land. You don't want to put it on your best acres for sure. But you need area for a wetland and a surrounding buffer. Having it be on the low spot in the field is great because we want to daylight the tile and we don't necessarily want to dig down 6 feet. We need soils that are capable of holding water. We need soils that can grow plants, but since you have been farming this field, we know it can grow things. So we just take that topsoil and put it back into the wetland after we dug out our basin. Having a prior converted farmland is preferred just because you have means it was a former wetland, so you have a native seed bank that is already there and maybe a slightly higher organic content, but not necessarily. But we can do this on upland soils. That is fine, or non-wetland soils. And if you're in a floodplain, you have to do a little bit extra, and you also have to consider bank stability. Let's talk about efficiency here. Now, wetlands in general, especially treatment wetlands, have been studied for 4 decades in different applications. I would say agriculture, we've been studying for maybe 20 years, maybe. Iowa has been studying their wetlands. It's a different design than what I described here, but they're seeing an average efficiency of removal about 40 to 90%. As Nathan mentioned, we have cycles through the year. When temperatures get cold, you have lower efficiency, but during the prime spring, summer, fall months, we are getting really great removal. The Nature Conservancy has been studying through wetlands for about 12 years now, and they're finding, and their wetlands are ranging in that 3 to 9% ratio. They're finding that their efficiency is 16 to 44%, but they also have some seepage. But if they account for that seepage loss, which technically is still removing nitrogen, they're to the 45 to 90% of removal of that nitrogen. We've been studying 2 wetlands for about 7 years of data, and we're finding efficiency between 21 to 69% for a wetland that's maybe between 1 to 1.8% ratio. And that's because we just didn't have a tile map, so we had to kind of, estimate the drainage area. And we have another wetland that's 3.6% of its drainage area, and we're getting much better removal there. So that's why I'm kind of indicating we think that 3% is kind of a key area. Now, I would just want to put a caveat when we're talking about efficiencies. It's a great way to do a comparison across practices, but with wetlands particularly, because where you can take base flow and we can take peak flow, we can actually have a really low efficiency, like we did in this year 1 where we had very little organic matter in our wetland as it was developing, and we had a really high removal in terms of pounds of nitrate going through the system, because we had, versus a year where we had a little bit higher efficiency in terms of removal, but we had a lower rate. And why is that? Because we're really talking about low removal depends on two things: the flow going through the system and the concentration going through the system. So if you have a high flow going through your system, say it's a very wet year, you had a high concentration of nitrate going in because maybe it was in corn that year, you can get a high mass removal, but a low percent removal, because you're just having a larger volume of water going through the system. And conversely, if you have low flow and low concentration, you're gonna have a low mass removal, but a high percentage in terms of removal. So it's just some different ways to look at efficiency. Sometimes that's not the all be all. So you have to kind of consider that, especially with tile treatment wetlands, we can measure different, is because it allows us to compare across practices, including infield and these conservation drainage practices. So just kind of end up on kind of the pluses and minuses here. You know, wetlands can remove nitrate and phosphorus to a point. They're a proven, really mature technology. We're just essentially tweaking some of the parameters right now. They're very effective and efficient. They can take both surface intake and surface runoff. Just once again, you have to have a bigger wetland. Require little annual maintenance, have a long practice life. Do not require any cropping system changes. And I guess the on-farm benefit would be you have some habitat, you can have some wildlife, some ducks, and a little bit of flood storage. And kind of the negatives are that they are expensive because you have to do some excavation. So I think next to recycling, drainage recycling, this is the second, you know, we're just under them because we have to do some excavation. So it has this high upfront cost. You know, it takes more than a day to implement. You know, it may take a couple of weeks to get it built. It takes land out of production, and it takes about 1 to 2 years to become really, I think, fully operation, kind of its max ability there. And of course, it can track maybe some species that you don't want. And so just to summarize, Nathan and I kind of put our data together and kind of do a comparison between the practices. But I think you can see overall, the typical nitrogen load reduction for these conservation drainage practices is very good. We're talking between 30 to 50% on average. So I will end there and take any questions, and Nathan can answer all of them.
Thank you, Jill. Thank you, Nathan. We are a little bit behind time, so I do see there's one question in the chat for Nathan, and it's how often do you need to replace the wood chips in a bioreactor? So maybe you can answer that while Laura pulls up her slides, and then I'll just quickly go to Laura's presentation.
Oh, good. So the correct answer is always it depends, right? No. We typically expect a 10 to 15 year life cycle on the wood chips, but it really does depend. If you have a system that tends to be dry, it's often dry, right? They'll decompose faster. Whereas if your bioreactor is usually full of water, those wood chips don't degrade as quickly, and they'll potentially last a lot longer. So overall, their bioreactors have been in for 10 or 15 years, and wood chips are still going strong. There's ones that have been in for less than 10 years and need to be refreshed because they're often dry, and the decomposition rate is much higher.
Thank you. All right. I am going to introduce our final speaker today is Dr. Laura Christensen from the University of Illinois. Dr. Christensen is a professional engineer, and she's an assistant professor of crop sciences at U of I's College of Agricultural, Consumer, and Environmental Sciences. Thank you very much, Laura, for joining us today, and take it away.
Okay, can you all hear me?
Yes, perfect.
Okay, good. Okay, well, Jill, Dr. Kostel set me up pretty well to round out the webinar for the last 10 minutes or so. I'm going to be talking about ways that we can compare different conservation practices. But before I get into these 6 ways that the practices can be compared, we'll talk about all 6 of those very briefly in this rapid fire last 10 minutes. I wanted to start with one of my favorite sayings. When we think about comparing conservation practices, no one practice will work for every acre. But of course, we want every acre to have at least one new conservation practice. We want as many practices as we can across the landscape. So let's start working our way down the list, starting with practice nutrient removal efficiency. That's probably the first and most obvious way that you would compare practices when we talk about water quality. And again, Jill set me up very well for this. Gosh, I wonder, do you see this little bar? I wonder if I can move that off. Okay, you see my full screen now. Okay, so this is a table that I've taken from our Illinois nutrient loss reduction strategy. Those of you in Illinois working in this space will be very familiar with all of these numbers. But for the rest of the talk today, we'll keep the same color scheme. The practices in blue are the infield management practices. Practices in green are the edge of field, or usually the constructed or conservation drainage practices that we're talking about today. And the practices in brown are our land use change practices. And again, those of you in Illinois will be very familiar with all of these numbers. We have practices from 10% all the way to 90% nitrogen loss reduction. And the practices we're focused on today, bioreactors in Illinois, have been rated at providing about 25% nitrogen loss reduction. Wetlands, much higher at 50% nitrogen loss reduction. The practice of controlled drainage and the practice of saturated buffers are not, as of today, officially recommended practices in the Illinois nutrient strategy, but we can get numbers from the other state strategies. For example, controlled drainage is rated at least 33% nitrogen loss reduction. So these numbers are pretty consistent with what Jill and Nathan both showed. Saturated buffers were recently added to the Iowa nutrient strategy, and the number they added for saturated buffers was 53% nitrogen loss reduction. Now, one thing that table doesn't show is that for any given practice, there is actually a range of effectiveness. So from a policy or a planning or an administrative perspective, it's very important for us as scientists to be able to put one number on a practice in terms of nitrogen loss effectiveness. But in reality, it's important that you realize that there's actually a range of effectiveness for any given practice in any given year at any given site. And so this graph helps illustrate that a little better than the table does. You see there's the dark blue bar, which is the mean or kind of the median value for that given practice. And then there's error bars. The lighter parts of the bars illustrate that there's a big range for some of these practices and how well they work in any given year. Moving on down the list, the next most obvious way to compare practices is how much does the practice cost, or thinking about it a different way, what's the cost efficiency of a practice? And this is very relevant for a lot of our landowners and farmers. One of the first things to think about when we talk about practice cost, often in different magnitudes for different practices. A good example is for bioreactors, I would say 95% plus of the cost of the practice occurs in year one when you build that practice. It's a very capital cost intensive practice. And then when you look at the design life, the rest of the 9 years or the rest of the 10 years, there's very, very small cost of that practice because there's a very minimal maintenance cost. You could compare that with something like a winter cover crop, which has an annual recurring cost. Relatively the same cost will reoccur every year that you do that winter cover crop. When those different costs, the different timing of the costs are taken into consideration, you can develop things like cost per acre in terms of amortized cost per acre, or cost efficiency, dollars per pound of nitrogen that we keep from going downstream. What we see for the conservation drainage practices, again, that we're talking about specifically today, bioreactors and wetlands are very cost effective. These are, again, numbers from our Illinois strategy. I think actually the $4 per pound of nitrogen might be a little bit high for wetlands, but when we add in controlled drainage numbers and saturated buffer numbers, cost efficiencies from the other states, really all four of these practices are very cost efficient in terms of dollars per pound of nitrogen that we keep from moving downstream. You might also be wondering, I don't just want to do one practice, I want to do a whole variety of practices across all of my fields. So how well do practices pair together? I like to think of that in terms of stacking. How well do practices stack together? What's the stackability? So for the next couple of slides, I'll talk about a study that we performed a couple years ago. If you're interested in these sorts of practice comparisons, I'm more than glad to provide this paper. But what you see, again, we have the practices listed down the left in the blue, the green, and the brown for the different kinds of practices. And when you look at their stacking scores, which we just assessed as scientists, don't get caught up in what the actual numbers are. They're just relative rankings for each practice. The green numbers, the higher stackability scores, pop up for the infield and the edge of field practices. That's because infield and edge of field practices pair with each other very well. They're very easy to do together. Now, when you look at the bottom of the table, the land use change practices actually don't stack with many of our other practices very well. So a practice like land retirement, which is the very bottom row in the table, that doesn't stack with, say, using a nitrification inhibitor, because that just doesn't make sense that you would use those practices together. So the land use change practices tend to be less stackable, but that's also a moot point because it's the land use change practices that also have the higher nitrogen loss reduction effectivenesses. You don't need to pair the land use change practices with anything else because you're already getting 80 or 90% nitrogen loss reduction. Another consideration, especially for our farmers and our landowners, is how easy is a given practice going to be to implement? Now, this is going to vary based on the farmer's own perception, but we also wanted to look at this in our study that we did. So we call this production system change. Now, in this new column that I just added to the table, a green value or a lower value, like with the nitrogen fertilizer management practices, that requires less production system change. So that might be easier to stomach in terms of a change to the production system for a landowner or a farmer. And you could compare that, again, don't get caught up in the numbers. These are just relative rankings. If you compare those green numbers to the red numbers, having a wholesale land use change of land retirement, that's a big ask for a lot of our, big conventional farmers. And so the red numbers are relatively harder practices to implement. And I think, as Jill mentioned, practices like wetlands can not just provide a water quality benefit, but a lot of additional benefits. And so comparing practices on ecosystem services or additional benefits is a very relevant thing to do. In this table, this is from a study we did back in 2014. 7 practices are listed across the top, and then we rated those practices based on additional ecosystem services, provisioning, regulating, and cultural services that those practices provide. Long story short, it's the practices that involve additional vegetation in the landscape that provide the most additional ecosystem services beyond nitrogen loss reduction. I also want to mention that the NRCS has rated all of their conservation practices in terms of physical effects. And so this can roughly be related to additional ecosystem services that these practices provide. But I think this is an excellent resource if you're interested to know how conservation practices compare in terms of the physical effects or the ecosystem services that they provide. The NRCS has done this already for all of their practices. You probably can't see that link, but I'll be glad to share the link if you're interested in this information. Now, lastly, practices vary in their ability for us to track them for reporting purposes. This might be slightly less relevant for individual landowners to consider, but for some of us working in this space, this tracking and reporting is very important. I'll remind you that it takes time, lag time, between when you implement a conservation practice on a given farm and when you actually detect a measurable improvement in water quality downstream, especially as far downstream as the Gulf of Mexico. So this lag time means that for us to continue to show progress towards our water quality goals, we need to track and report what conservation practices we are actually doing in the landscape to show progress towards those goals. And so we've also thought about how hard or easy is it to track any of these given conservation practices. So for example, practices that are privately implemented decisions, typically like nitrogen fertilizer management, those are practices that are actually really hard for us to track across the landscape unless you do something like a survey. And even then it's not real easy to get a perfect picture of how nitrogen fertilizer is being managed. Now compare that to practices like bioreactors or wetlands that are typically built with assistance from federal funds. That's easier to track those practices. And then things like land use change are easy to track via satellite imagery. So I'll end where we started with one of my favorite slogans. Again, no conservation practice will be suitable all the time for every single acre in terms of comparing practices, but we do just want lots and lots and lots more conservation practices across our landscape. Thanks a lot. Back to you, Adrienne.
Thank you very much, Laura, and thank you to all of our speakers today. We are running up on our 12:15 end time, so unfortunately we don't have a lot of time for questions today. I see some have put questions in the chat, and we will try to address those with our speakers and get answers back out to you. In the meantime, I just wanted to let you know we will be following up with you with a recording of today's presentation. And I would like to invite you to all come back next week for our next session, which is going to explore conservation drainage at the practice scale. It's going to kick off at the same time next Thursday, 11 a.m. The same link you used to join today, you can use that same link again next week. And then finally, for anyone who would like to receive continuing education credits for participating today, there are 3 options on the screen for you to access those. And additionally, before you leave, I'm going to launch a very quick poll. It's going to pop up on your screen. If you could just help us improve these sessions for next week, the next 2 weeks, that would be very helpful to us. And thank you again for your attention today. Have a wonderful afternoon. And if you did have any outstanding questions, you can feel free to enter those in the chat and we will do our best to address them as soon as possible. Thank you.
Thanks, Adrienne. Thanks, everyone.
Thank you. Have a good day.